Mr. Muhammad, Mr. Sacha. This is the operator norm. Okay? The supremum of all t of x known whenever x belongs to x and the norm of x is less than 1. We have then BL of y with the operator norm defined in a star is a norm space. Okay, this is evidently a vector space, and this is a norm function on this vector space. So we have a norm space. Also, if Y is a Banach space, this space, this norm space is a Banach space, then BL of x and y with the operator norm is a Banach space. Okay? It is not that it is very trivial that B of x and y is a vector space or linear space, because if T1 and T2 are two bounded linear functions from x to y, then T1 plus T2 is a bounded linear function too. And for any alpha T1, for example, is a bounded linear function from x to y, and T1 plus T2 is this function for any x equal to T1 of x plus T2 of x, and alpha T1 of x equal to alpha multiplied by T1 of x. It is very trivial that if T1 and T2 are linear, T1 plus T2 is linear too, and if T1 and T2 are bounded, then T1 plus T2 is bounded too, also for alpha T1. For boundedness, we see that if x belongs to x and the norm of x is less than or equal 1, then this norm in y, T1 plus T2 of x, equal to T1 of x plus T2 of x, and this norm is less than or equal this summation, because this is a norm in y, and any norm have triangle property. This is triangle inequality in the norm of y, T1 of x plus T2 of x. And we know that this norm is less than or equal the operator norm of T1, because the operator norm of T1 is the supremum of all of these norms, because we consider x with this property. The supremum of all of norms equal to the operator norm of T1, and also this is less than or equal the operator norm of T2. So that for any x with this property, this is less than these real numbers. So the supremum of all these norms is less than or equal this real numbers. But the supremum of this equal to the operator norm of T1 plus T2. For any x we have this. So that the operator norm or the supremum of this norms is less than or equal to this. The supremum of this equal to the operator norm of T1 plus T2. And the point of this norm properties of this operator norm is very easy, because for example we see that for any bounded and linear function from x to y, the operator norm of t is non-negative. It is very trivial, because the operator norm equal to this supremum, and all of these objects are non-negative, so that its supremum must be non-negative, so that this norm or this value is non-negative. Also, if t equal to 0, we have the operator norm equal to 0, because if t equal to 0, all of this must be 0, and the supremum of 0 equal to 0. All of this must be 0, so that this set is 0 only. Conversely, if the operator norm of t equal to 0, then this supremum must be equal to 0. And since all of this is non-negative, all of this must be 0. This supremum equal to 0, and all of this object is non-negative, so that all of this must be 0. For any x, this norm must be 0, equal to 0. So that for all x, t of x must be 0, so that t is the constant function 0. And by these two we have t equal to 0 if and only if the norm of t equal to 0. The operator norm of t equal to 0. Okay? And this is very easy, that if this supremum equal to 0 for any x, the norm of t of x equal to 0, because the supremum is only for elements of x with this property. On the other hand, if t is a linear and bounded function from x to y, and alpha be a scalar, the operator norm of alpha t equal to this supremum of the norm of alpha t of x, such that x belongs to x, and the norm of x is less than or equal 1. But this supremum equal to this supremum. alpha t of x, okay, and this is equal to the absolute value of alpha multiplied by the supremum of t of x, such that x belongs to x and the norm of x is less than or equal 1. But we know that this supremum equal to the operator norm of t, so that the norm of alpha t is less than or equal the absolute value of alpha, the norm of t. And finally we have triangle inequality. We proved triangle inequality in the previous slide. We have triangle inequality, and t is the norm of t is non-negative, and the norm of t equal to 0 if and only if t equal to 0. And also we have these properties, so that BL of x and y with the operator norm is a norm space. We have this definition. If x is a norm space, then the dual space of x, denoted by x star or x prime in some books, this denoted by x prime, okay, dual space, and defined by the set of all bounded and linear functions from x to f. If the definition of BL of x and y, we consider y equal to f, the field of scalar numbers, then we have the dual space of x. The dual space of x equal to the set of all bounded and linear maps from x to f. For any norm space x star with the operator norm. This is with the operator norm is a Banach space, because we know that f is a Banach space. We say that if y is Banach, then this is a Banach space. X star always is a Banach space, unless it's not Banach or not complete. Okay? And we have these equalities for the operator norms. Operator norm equal to this supremum or this supremum. The supremum of all t of x norms such that x belongs to x and t of x equal to 1, not less than or equal. And these two are equal to this infimum, the infimum of all m, such that for any x, this norm is less than or equal m multiplied by the norm of x. All of these are equal, and this proof is easy, and you can find in all functional analysis books. Also, a linear map such as t from x to y is bounded if and only if it is continuous. Okay? Boundedness and continuity in linear maps are equal. Dear students, do you have my voice? Okay. Boundedness and continuity for linear maps are equal. Let T be a bounded and linear map from x to y. Then for any x in x, we have this inequality. The norm of t of x is less than or equal the norm of t multiplied by the norm of x. Please note that if x equal to 0, we know that t of 0 equal to 0, so that the norm of t of 0 equal to 0, and this is less than or equal 0, so that we have this inequality for x equal to 0. And if x is non-zero, we see that this is equal to this node, because this can be considered as an alpha, and this is the norm function, and this is equal to this because t is a linear map is equal to t of alpha x, and this is less than or equal than operator norm of t, because we know that the norm of this element is equal to 1, so that this is less than or equal the norm of t. If you multiply this real number in each side of this inequality, we see that this is less than or equal the operator norm of t multiplied by the norm of x, so that we have this useful property. If t from x to y is linear, the following are equal: t is continuous, or the next is an element such that t is continuous at x0. This is very nice too for linear maps. Continuity at one point equal to continuity in all domain. Continuity in one point equal to continuity in all points. Continuity in one point equal to continuity in all points. Okay. Let X be a Hausdorff topological space. Put C of X equal to the set of all f from X to C such that f is bounded and continuous. C0 of X is a subset of C of x that have these additional properties for any epsilon. The set of all x by this property is a compact subset. We say that C0 of x is the set of all continuous functions that are vanish at infinity. Vanish at infinity. Vanish at infinity. C0 of x. And C double 0 of x is the set of all functions from x to c that is f is bounded and continuous. And the support of f is compact. The set of all f from x to c that is bounded and continuous, and the support of f, the set of all x such that f is non-zero, f of x is non-zero, must be compact. It is very trivial that C0 of x is a subset of C double 0 of x is a subset of C0 of x, and this is a subset of C of x. Okay? Please note that let x be a Hausdorff topological space. Okay? F is a subset of x if and only if f is bounded and continuous and we have this property for any epsilon. This set is compact. And this holds if and only if f is bounded and continuous and for any epsilon there exists a compact subset of x compact. or we can say that X is a subset such that K is compact and for any X in X minus K we have this property. These two are equivalent because if we have this property you can consider this as this K. By our assumption this is a compact, so that we have a compact subset of X such that for any X outside of this set we have the absolute value of f of X is less than epsilon. Okay, and conversely if we have this property then this is a compact set because this is a subset of K. Please note that if K have this property then if we have this property then the set of all X such that f of X is greater or equal epsilon is a subset of K. Because this means that if X not belong to K, f of X is less than epsilon, so that if f of X is greater or equal epsilon then X must be belong to K. You know that P of Q equal to P then Q equal to the negation of Q then the negation of P. Okay, P and Q, the negation of Q, the negation of P, and this shows that this is a subset of K. No, since K is compact, since this is a closed subset of X, this must be compact. Okay, in any host of a space, any closed subset of a compact set in Hausdorff space in Hausdorff space is a compact set. Okay, we use from this property so that these two are equivalent. For any epsilon, the set of all x with this property is compact, or for any epsilon there exists a compact subset of x such that for any x outside of K we have this property. For this property we say that f vanish at infinity. Okay, f must be vanish at infinity. Vanish at infinity. Vanish at infinity. For any epsilon there exists a compact set. Okay, compact set such that all subset of this f of x must be less than epsilon. Okay, so that we say that f vanish at infinity. Let beta be a Borel sigma algebra on X. Recall that beta is the smallest sigma algebra that contain all open subset of X. The sigma algebra generated by open sets is called Borel sets, or the sigma algebra of Borel sets. The smallest sigma algebra that contain all open subsets. So if T is the topology of X, then beta is the smallest sigma algebra that contain tau, or beta is the sigma algebra generated by tau, and any element of beta is called a Borel set. A Borel set. We have this definition. A Borel measure on X is a measure on beta. A Borel measure on X is a measure on beta, or the sigma algebra of Borel sets, and if mu from beta to this interval is a measure, we say mu is a Borel measure. Definition: mu from beta to this interval is called regular whenever for any open subset of X mu of O equal to the supremum of mu of F for any compact subset of O, and for any Borel subset of X mu of U equal to this infimum, the infimum of all mu of O, such that O is open and containing U. So that if we have this to equality, then we say that mu is a regular Borel measure, regular. This called internal regular and this called external regular. But if we have these two properties, we say that mu is a regular measure. It is not that for any compact subset of O, if F be any compact subset of O, we know that mu of F is less than or equal mu of O. Because we know that any positive measure is monotone. So that all of these objects is less than or equal mu of O. Okay? Now in regular measures, the supremum must be equal to mu of O exactly. And also for any open set that containing U, if U is a subset of O, mu of U is less than or equal mu of O. Mu of U is less than all of these objects. But in regular measure, the infimum of these elements must be equal to mu of U exactly. Okay? So that it is very trivial that the supremum is less than or equal mu of O. Because all of this is less than or equal mu of O. The supremum of this is less than or equal. But in regular measure, the supremum must be equal to mu of O. And also, it is trivial that this infimum is great or equal this measure mu of U, because all of this is great or equal, so that its infimum must be great or equal. And in regular measure, these two are equal. Now, we can define complex regular measure. A complex measure such as mu from beta to C is called regular whenever its absolute value be regular. Okay? If this is a regular measure, we say that mu is regular, and the set of all complex Borel regular measures from or on X denoted by M of X, the set of all Borel regular measures denoted by M of X. Please note that for any Borel regular measure such as mu, if we define f mu from C0 of X to C by this function rules, f of mu of f equal to this integral, so that this function maps f to this integral. Any f maps to this integral of f with respect to mu on X, and this is the Lebesgue measure, and you Know this integral f of mu from c0 of x to c. F mu of f equal to this integral. F mu is linear and bounded. Linear and bounded. So if please note that for any f and g in c0 of x, f mu of f plus g equal to this integral. The integral of f plus g d mu, and this equal to the integral of f plus the integral of g. But this is equal to f mu of f, and this is equal to f mu of g, so that f mu is bounded, and also it is f mu is linear, and also it is bounded. Linear and bounded. The maps mu maps to f mu. No, we consider another map. This is f mu as an element of the dual of C0 No, we consider this map is a function from m of x to the dual space of C0 of x. In the next important theorem, we see that this function is onto, and this is the Rees representation theorem, and this theorem is very important. Before, let me recall this definition. A Banach space X, and this is called a Banach algebra whenever a Banach space is called a Banach algebra whenever there is a binary operation such as a star on x, such that for any x and y in x we have this inequality. The norm of x star y is less than or equal the norm of x multiplied by the norm of y. So that in Banach algebras, not Banach space, we must have three binary or three operation: addition, a star, and a scalar multiplication. Okay, we have two binary operation and one a scalar multiplication. But in Banach space, we must have only a vector space, and so we have only a binary operation and multiplication. In Banach algebra, we need another Binary operations such as star plus from x times x to x, x and y maps to x plus y, scalar multiplication from f times x to x, and a star from x times x to x that maps x and y to x star y. Let G be a locally compact topological group, then by the Rees representation theorem, the dual space of X C0 of G equal to M of G. I write this theorem for you. The Rees representation theorem, that X be a locally compact topological space, and for any Borel regular measure mu, we define f mu from C0 of x to z by this function rules, f mu of f equal to this integral. Then this function is in the dual of C0 of x. This is a part of this theorem. Moreover, the functions maps mu to f mu is an isometric isomorphism from m of x to C0 of x prime or C0 of x star with this norm, so that the dual of C0 of x equal to m of x, and this is the Rees representation theorem. Okay, Rees representation theorem. In the next session, we see that this is a m of x is an algebra, okay, is an algebra. And so this function is a Banach algebra isomorphism and isometrically isomorphous functions. Isometrically isomorphous, and you know that this means that for any mu in m of x, the norm of f mu equal to the norm of mu, and this is the operator norm, because we know that f mu is a function from C0 of x to c, and this is a functional, bounded and linear, and this norm is the operator norm of this bounded and linear function. these two are equal, so that this map is isometric, and these two are isometrically isomorphism. Okay, dear students, do you have any question for? Goodbye.